attempt to join for specific talks. So for
recording in progress.
Okay. The minute we have before the exact time, perhaps Gianluca Lippi, as organizer of this specific work, if you want to say an introductory word, or
it's not important, but thank you very much. I'll be extremely quick. Thank you to everybody for coming to this session. Thank you for participating. It is a transition year because the person who was in charge of the seminar has quit, but very short notice. So I just picked it up and we tried to put everything together as we could. Next year we'll do much better by informing people in advance. Thank you very much, and go ahead, please.
Okay. So that was exactly the minute. Gianluca is perfectly capable of creating a 1-minute introduction upon request. So we are ready to start this session of the second day. The first talk will be given by Carlo Silvestri, formerly from Politecnico di Bari and now in Brisbane in Australia. And the talk will be about self-detection near-field optical microscopy based on terahertz quantum cascade laser. Go ahead, Carlo.
Thank you. I just want to mention that this work is a collaboration with Lorenzo Columbo from Politecnico di Torino and Massimo Brambilla from Politecnico di Bari. In the first part of the talk, I will introduce the topic, and then I will describe the typical layout for the configuration, self-detection, scattering SNOME that will be the object of this study. Then I will present a theoretical model that we use to model this configuration, which is the Lang-Kobayashi equation with a complex scattering coefficient. And then I will present the reconstruction method for the dielectric permittivity of a material sample that we introduce in this work. And finally, I will draw the conclusion of the study. So quantum cascade lasers are semiconductor laser invented at the Bell Labs in 1994, and they can emit in the mid-IR and in the terahertz spectral ranges. They are unipolar devices because they are based on transitions between confined states in the conduction band, which are named subbands. And also they rely on resonant tunneling, electron phonon scattering processes, and through band gap engineering, it is possible to tailor the emission properties of these lasers. The first element of the configuration that we are going to study in this work is the self-mixing, in particular the self-mixing in quantum cascade lasers. So quantum cascade lasers have peculiar physical properties, such as the lower carrier lifetime with respect to conventional laser diodes, and also lower alpha factor with respect to bipolar laser diodes. This imply higher damping of the relaxation oscillation and lower coupling between amplitude and phase of the electric field, respectively. And the consequence of this is that these lasers exhibit higher stability of the single mode emission under strong feedback. And this has been exploited for applications in sensing, vibrometry, optical communication, and so on. From a mathematical point of view, we describe the self-mixing with the Lang-Kobayashi model, which is a rate equation model where the dynamical variables are electric field and density of carriers. And a delayed term in the equation for the electric field models the presence of the feedback in the configuration. Also, a C parameter, also called Hackett parameter, quantifies the level of feedback of the configuration. The second element of the technique studied in this work is the scattering type near-field optical microscopy, which is a microscopy providing a high resolution beyond the diffraction limit. And it's based on near-field interaction between an atomic force microscope tip and the material sample that we want to analyze. In particular, we are interested to retrieve the optical properties of this material sample. And the near-field interaction between this tip and the sample is mediated by evanescent waves, so that the diffraction limit is circumvented and the resolution is only limited by the size of the tip, which is typically tens of nanometers. In our configuration, we will consider a terahertz quantum cascade laser as a source. So by combining self-detection and SNOME, we obtain the self-detection scattering SNOME, which is a technique presenting two main advantages. The first one is comes from the self-detection part, which is possibility to overcome the lack of efficient detectors in the terahertz range, because the QCL is used both as laser and as a detector. And the SNOM part implies a high resolution beyond the diffraction limit. And a typical configuration of this technique is shown in this slide. Just I mentioned that this technique was firstly introduced in 2018 by the group of Miriam Vitiello. The field, the light emitted by the terahertz QCL is conveyed onto the target composed by tip and sample, and then the near field interaction generates a scattered field which is reinjected into the laser cavity, and the interference between the reinjected field and the intracavity field change the emission characteristics of the laser, like emission frequency, power, and voltage across the laser terminals. In particular, by measuring the voltage signal, is it possible to retrieve the properties of the target and reconstruct the dielectric function of the material, the analyzed material, with nanometric resolution. Another detail of this configuration is the fact that the tip is in tapping mode, so it oscillates. And this is due to the fact that we want to demodulate the signal and retrieve the harmonics of the signal through a lock-in amplifier present in the configuration. We want to do this because in this way, we can isolate the harmonics which contain the pure information about the near field interaction, excluding the ones containing the spurious background. The mathematical description of this configuration is done through the Lanko-Bayashi equations with a complex scattering coefficient. So in the coupling term appearing multiplied by the delayed field in the equation for the electric field, we have this factor sigma, which is a complex scattering coefficient with modulus S and phase phi. So this scattering coefficient sigma includes the properties of the sample, as we will see in the next slide. And it is the quantity that we want to preliminarily determine in order to obtain the dielectric permittivity. Since the temporal variation of the feedback is slow compared to the field and carrier dynamics, which means that the oscillation frequency of the tip is slower than the typical carrier and field dynamics of QCL, we can use the steady-state solutions of the Lanko-Bayashi model. And in particular, we have a signal equation where delta V is the voltage signal across the laser terminals, and the phase excess equation, where the emission frequency perturbed by the feedback is related to the emission frequency in absence of feedback. And both these equations include the modulus and phase of the scattering coefficient, so that by measuring the signal, is it possible to extract the information of the scattering coefficient and then on dielectric permittivity. In this slide, I explain a bit better the link between the scattering coefficient and the dielectric permittivity. The near field interaction between tip and sample in the SNOM can be described by a model called finite dipole model through an effective polarizability. This effective polarizability of the tip sample target depends on this epsilon s, which is the dielectric permittivity of the sample. So considering that the scattering coefficient is proportional to the effective polarizability, and also the scattering coefficient appears in the signal equation, in principle, by measuring the signal, is it possible to retrieve the dielectric function by walking this opposite path highlighted in red. And now I will describe the method that we use to retrieve the scattering coefficient. So our starting point are the steady-state solution of the Lanko-Bayashi model. We introduce a Fourier series expansion for scattering coefficient and signal so that we work with the harmonics. And then by performing a first-order Taylor expansion of the phase excess equation, we can determine a first-order approximated expression of the signal. And we noticed that in the very weak feedback regime, which corresponds to Hackett parameter C lower than 0.1, is it commonly used the zero-order approximation. So this omega f is equal to omega 0. But in our theory, we are adding a first-order correction, which allow us to consider to taking into account a higher feedback, so that we can consider a description of the whole weak feedback regime corresponding to C lower than 1. So we have a first-order approximated expression of the signal. This quantity depends on the external cavity length, which is the distance between the laser and the target. And we can shift this external cavity length L by fixed quantities, lambda over 8, lambda over 4, and 3 lambda over 8, where lambda is the free running wavelength of the laser, so that we can obtain 3 expressions for shifted signal. And then by combining these 4 obtained signal, we can determine explicit formulas for the retrieval of modulus and phase of the scattering coefficient harmonics as a function of the signal harmonics. And we recall that the signal harmonics are the quantities which are experimentally measured through the locking amplifier. Then we can compare the very weak regime formulas with the weak regime formula. In the very weak regime, we have zero-order approximated formulas, as I previously mentioned, which are based on 2 experimental measures. So by measuring 2 signals, it is possible to retrieve each harmonic of the scattering coefficient. And these are generally used to interpret experimental data. In this work, we added like a first-order correction. So by measuring 4 signals, we can retrieve the modulus and phase of the harmonics of the scattering coefficient. So we have a higher number of measurements to be performed, but we can account for higher feedback. And this is advantageous for the experiment, because in the weak regime, we have a higher signal-to-noise ratio. Then we tested these formulas on numerically simulated self-mixing signals. So we simulated the configuration by supposing a sample of cesium bromide, which has 2 formal resonances. And the numerical procedure is explained here. So we choose a set of emission wave numbers of frequencies, and for each emission wave number, we solve the Lanko-Bayashi equations in the weak feedback regime. And then we shift the external cavity length, and we obtain also the shifted signals. And by combining all these obtained signals, we can reconstruct modulus and phase of the scattering coefficient harmonics. And we use zero-order formulas and first-order formulas to compare between each other. And also we want to compare them with some reference curves. And in particular, we calculated the harmonics of the scattering coefficient by using the finite dipole model. So we have 2 reconstructions and some reference curves obtained by calculation. Here we show the results for the 3rd harmonic of the scattering coefficient. So S3 is the modulus and phi3 is the phase of the 3rd harmonics of the scattering coefficient. And the blue curve is the reference curve. The black one is the reconstruction at 0 order, rigorously valid in the very weak feedback regime. And the red one is the reconstruction at the 1st order. And we can notice that there is a good agreement between reconstructions and reference curve, but from this in zoomed in boxes, we can see that the 1st order is almost overlapped with the reference curve. So the 1st order approximations results better than 0 order approximation as expected. And then from the harmonics, we can reconstruct dielectric permittivity. And in particular, here I show the real part of the dielectric permittivity of cesium bromide. The black curve is a fit of experimental data extracted from a textbook. And the red curve is the reconstruction performed with our method. And in particular, we are interested to estimate the frequencies of the phonon resonances, which correspond to the zeros of the real part of the dielectric function. And we can see that we can estimate the transverse optical phonon frequency with an error of 0.1% and the longitudinal optical phonon frequency with an error of 0.07%. So there is a good accuracy provided by our model in the estimation of the phonon frequencies. So this is the conclusion. We theoretically studied the self-detection S-SNOW configuration by using the Lanko-Bayashi model with a complex scattering coefficient. And we derived an approximated method to reconstruct the dielectric permittivity of a sample. The proposed method is valid in the weak feedback regime, and it is based on a first-order approximation of the phase excess equation. Then we test this method on two numerically simulated self-mixing signals, and we were able to estimate the phonon resonances of a supposed sample of cesium bromide with good accuracy. This method can be applied to experimental traces with analogous benefit. Thank you.
Okay, thank you very much, Carlo. Thank you for this first talk. Are there any questions in the audience? I have found how to raise hands. So down there is a reaction with a little smiley face. And in the reactions, you can shout or cry or send hearts, and you can also raise hand. So if you want to raise your hand, please do. And yes, Vladimir Kocharovsky, please go ahead.
Hello, as I understood, you use a monochromatic signal from external source, QCD, and would it be reasonable to use the source with harmonics itself? So in the source you can have third, for example, harmonic, and may it be possible to increase the signal you want to receive in the nonlinear regime?
So yeah, we use a monochromatic source, and then we decompose harmonics in order to exclude, like, for example, the zero order or first order harmonics, because they contain the background, which is not directly related to the like the near field interaction. So this background doesn't bring any information about the sample. For this reason, like we exclude these harmonics, and we want to retrieve, for example, the harmonics, the third harmonic, as I show in the slide, because in the third harmonic there is no background, and you can really have the information on the permittivity of the material, let's say. To increase the power of the signal, we should increase the feedback level. But if we increase the feedback level beyond the weak regime, we enter the moderate regime, where the characteristic of the signals are different, because there is there are multiple solutions of the phase excess equations. So the theory cannot be treated with this like method that we used here. But we didn't study the moderate regime. So,
okay, I see. Thank you.
So this method is valid only when the phase excess equation has a single solution. So until C = 1, we can use it.
Thank you. I see.
Thank you, Carlo. Are there other questions? Yes, Gianluca, please.
Yeah, thank you. Very good question. Very impressive. Thank you very much. Given the amount of parameters I saw in the model, I wonder if you apply that to experimental signal, what is the stability? The test you gave on the model is very convincing, but I wonder, when in the presence of experimental noise, how stable the scheme will be.
Actually, this first order theory, we applied it to, I mean, here we use it to theoretically reproduce the dielectric permittivity. But for example, if we limit only to the retrieval of a single harmonic, for example, the third one, and we choose a single frequency, and we can vary the external cavity length, we can do actually an imaging of a sample, and we can determine, for example, measures of contrast. For example, if we have a material like a structure composed by two materials, we can map a contrast. And we test this method on in a paper, APL Photonics of 2 years ago, to analyze some gold structures. So there was the experimental part performed by the group of medium Vitello, and exactly these formulas were applied to have like some measurements of contrast. And there was stability. The problem in that specific experiment was that by comparing the zero order and the first order, there was not like a relevant improvement in it, in that particular experiment. But the stability was so we have some reference curves, and we try to fit these reference curves with our parameters. Once we found the suitable parameter set, then we replicated the theoretical analysis for all the other curves. And there was stability, but the improvement passing from the zero order to the first order was minimum.
Thank you.
Okay, thank you, Carlo. If you're available later on, I may have a question that we can discuss in 1 minute. But for now, let's go for the next speaker. Many thanks, Carlo, for opening this session. So you can then remove your screen, please, Carlo, and Professor Zverev, please go ahead. So the second talk will be given by Professor Zverev. It will be about cooperative excitation of terbium ions in mostly carbon fluoride crystals.
Can you see my presentation?
I can, yes. I suspect others also can. Go ahead.
Yes, yes.
Okay, good. So I will talk about the cooperative excitation of the terbium ions in calcium fluoride, terbium fluoride, and with the terbium fluoride crystal. So it's like a kind of complex crystal that we have prepared here in our institute. And here are the co-authors of my work. Anastasia Nekhoрошев, she made some spectroscopic investigations. Vasily Konishkin, she was responsible for growing the crystal, and Anatoly Sirotkin for making some discussion and organizing this work. So, let me try. Yes. So the outline of my talk will be, at first I'll talk a little bit about some laser radiation invisible that is necessary for many practical applications. Then I will talk about rare earth ions and host materials that are perspective for visible solid-state lasers, and talk about the terbium laser system, spectroscopy, some analysis, and then there will be a conclusion. So, well, application, of course, I think that in this audience, it's not necessary to talk about all these ideas about practical applications of visible lasers, because, of course, many laser systems are necessary for medicine, for entertainment, scientific, adaptive astronomy, military, and in many cases it is necessary to have a special wavelengths, optimal wavelengths for operation of the certain system, and have some specific interaction with the material. And also it is necessary to use a certain power level of the laser system, and that's why it is necessary to think about this. Especially, well, we worked a little bit with some medicine applications of visible lasers, and for example, well, for cosmetic surgery, it is necessary to use lasers that work in visible range, because we all know that the water has low absorption in visible range, but if we speak about hemoglobin, melanin, so oxyhemoglobin, they have some peaks here. Here is the logarithmic scale, by the way, and that's why it is necessary to have the system working in the green and yellow spectral region. And so here there are some practical applications of some hair removing or removing of tattoos or some birthmarks. And this is because the different wavelengths of the laser radiation with different wavelengths transmits, has different depth of transmission. And this is also because of hemoglobin that absorbs the laser radiation. Of course, well, such applications like entertainment, projection systems, they are also very interesting and useful. And well, in the science and Raman spectroscopy, of course, we all use these laser systems because the silicon detectors are very popular. They have very high spatial resolution. That's why, and sensitivity. That's why we all normally work in the visible spectral range. Of course, if we talk about commercial solid-state lasers and visible, right now there is a huge amount of different lasers that are available. Of course, we need to start from a Rabi laser that gives red radiation. Then there are a great number of semiconductor lasers. Now they operate at all wavelengths. Recently developed gallium nitride laser that operates in blue is very interesting perspective and widely used now for excitation of other laser systems. Tunable lasers in dye, in solid polymer. It also works like a solid laser system, while dye can be destroyed in the polymer matrix. Tunable lasers like sapphire, titanium, well known. Most of the lasers that we use and that are commonly used, they use neodymium laser as the source of fundamental radiation, and then they have second and third harmonic radiation that gives us the certain wavelengths that are written here. Of course, well, there are some frequency Raman lasers that can produce slightly different wavelengths that are required. But of course, well, the aim is to develop a reliable solid-state source that can be used in widely in many practical applications at certain wavelengths without any complex nonlinear processes, all this kind of things. And compared with semiconductor systems, of course, well, solid-state lasers, they can produce higher peak intensities. That's why they still can compete with these semiconductor systems. And of course, they have a low spatial divergence, and are, in this case, they are very attractive. Of course, well, if we just look at the energy diagram, we can choose certain materials, certain rare earth ions that can give us the visible radiation. And here I show just the number of these rare earth ions. But we choose for our experiments, we choose terbium ion because it has rather interesting energy scheme, as there is a 5D4 energy transition that gives us the rainbow of different wavelengths. And the most intensive wavelength is the green one that works at 540, about 540 nanometers. This material can also be excited by the blue diode lasers operating at 380 or 485 nanometers, this direct transition. But of course, well, it is necessary. Well, it is not so easy to obtain and to develop a terbium laser because there are some drawbacks in different host materials. I'll talk a little bit later about this. So, speaking about the excitation of terbium, it's possible to choose different approaches, and it's possible either to work with a direct excitation, but it's necessary to understand that if you use direct excitation, then the radiation that you will use is a blue or UV radiation. That's why it is very close to the absorption band, the fundamental absorption band. And if you want to have high power, then there can be 2-photon absorption that can limit your power, output power of your laser. Then there can be up conversion. Up conversion can also be interesting for terbium, but most of excitation processes of terbium are connected with the energy transfer from either from material from that is excited that is excited somehow. For example, for praseodymium, it is possible to excite in a two-step process, and then there is the energy transfer from praseodymium to terbium, and then you can get the laser radiation. If we use ytterbium, ytterbium is interesting, and ytterbium in together with terbium can arrange this cooperative excitation so that two excited ytterbium ions can give you can transfer this energy, some energy, to one terbium ion. So there can be different, but it also depends on the host material that you use, and that's why there are special requirements for the host materials. Well, there are good optical qualities and low absorption and so on. No scattering, good mechanical properties, technical. There should be some places for active ions that can allow introducing parameters of the active ions. There should be places for the active ions in the matrix structure, and also there should be the technology of growth of this material. Also, it is necessary to mention that to reduce the probability of multi-phonon processes, it is necessary to use materials with a short phonon spectra. So, speaking about the 2-photon absorption in blue spectral region, well, it is necessary to mention that blue light can give, for example, in oxide materials, they have very high 2-photon absorption. That's why they are not so useful for this material. And fluorides, and so we choose fluoride material, calcium fluoride. It has very high, very large energy band gap between the valence and the conduction band. That's why not much 2-photon absorption is observed in this system. So in our lab, we prepared the concentration series of calcium fluoride crystals with terbium and ytterbium. Here is the parameters of the concentration that we prepared in our lab. And here are the absorption spectra of these samples. So you can see here that this is the ytterbium absorption line in the mixed crystal, and here are the absorptions of terbium with in the samples with different concentration. And this well fits the energy scheme of our system. And we use the Jadot theory in order to analyze the spectroscopy properties of our ions in calcium fluoride. We calculated the strength, and we compared the strength of separate lines with the theoretical lines, and estimated the Jadot parameters that were found to be to fit well with the other with other published data that I found in other fluoride materials. And it was possible for us to estimate the probability of the transmission and to get the spectral parameters for the emission spectra. Here are the probabilities of the emission from the 5D4 level, upper level to the low-lying levels, and here are the probabilities of the certain transitions. So you can see here that this transition at 543 has much higher probability, and this fits well with the parameters that we obtained in our emission spectra. So this green line is much stronger than all other lines. This spectra was obtained with the irradiating by the diode with the wavelength of 450 nanometers. And what is beautiful and interesting was in this work is that when we irradiated our sample with the laser diode working at 960 nanometers, so here is the picture of our experiment, and we irradiated with the with this laser diode that is shown with red, and so we observed the intense radiation in the at about 1 micron. That is the emission of ytterbium ions. But when we put the colored special filters, so we observed very intense this green radiation that was observed visually. We can observe visually, and this is the lines that corresponds to terbium ions in this laser system. So we checked the intensity dependence of these green lines of terbium in our system compared with the excitation from laser diode at 946, and we got the square dependence that really proves that the excitation of the terbium goes in a cooperative energy by cooperative energy transfer from two ytterbium ions, and they gives us the excited terbium ions, and they gives us this terbium radiation. Well, I come to the conclusion. So I must say that our work showed us that it is really interesting and possible to investigate and to try to develop the visible laser operating in the calcium fluoride crystal activated with terbium and deuterium ions. And of course, I know that there are also other many other publications on this topic, but they are mostly made experiments on oxide materials. Oxide materials, they have limitations on this kind of energy transfer from ytterbium to terbium. That's why we think that our work has some practical importance, and well, of course, we need a little bit further investigations in order to find the optimal concentration of our dopants for effective cooperative energy transfer process. And I think that we will be able to develop this efficient medium for diode pumped lasers. I must say that, of course, it is much easier to pump this solid state laser with a well-developed laser diodes working at 960 nanometers, because well, laser diodes that operates at 450, they have still some limitations, and that's why I think our work will be still have some practical interest. Thank you for your attention, and well, I'm ready to answer some questions.
Okay, thank you very much. There won't be much questions because we are a little bit tight on time. We have 1 minute. We can take 2 minutes, of course. If there is a question, please raise your hand, or if you don't find the knob to raise your hand, just open your microphone and talk. So while someone else may be looking for the phone, I do have a question. Actually, I was wondering, what is the plan to optimize the concentration? So I understand from some concentrations, you can calculate pretty well absorption and emission spectra. But can you go the other way around? So what is the process you can use to optimize this material?
You see, well, it is interesting that in this material, well, the ions, the radius of the active ions are very close to calcium, to the radius of the calcium ion. That's why it is rather easy to make rather high concentration of doped ions. And that's why we made these experiments with a sample that has about 5% terbium and 5% ytterbium, but also right now we have also samples that have concentrations up to 10% of terbium and something like 10% of ytterbium. So we need to check and to see whether this high concentration can help us to arrange this efficient energy transfer in this material. And it's also interesting that there is there is no concentration quenching in terbium ions, and that's why it's really possible, like we have in, for example, neodymium ions. That's why really possible to have very high concentration of ions.
Really some tries, some attempts, but there is room for improvement. Excellent. Thank you very much then for the talk and for answering this question. We will then now switch to the next speaker. The talk will be given by Vladimir Kocharovsky, who joined. Okay, thank you. And the talk will be about spontaneous symmetry breaking of the superradiant states and the effect of sideband modes in this instability. If you want to share your screen.
Let me share my screen. Okay.
Yeah, I can see it. Yeah, that's perfect. Excellent.
Fine, thank you.
Go ahead.
Let me shift from the very practical applied problems of the previous talk to the rather general fundamental physical problem. I'll discuss the phenomenon of spontaneous symmetry breaking of the laser. You know that in standard lasers, if we have symmetric Fabry-Pérot cavity, then the lasing is also symmetric. The radiation is the same from both ends of the cavity. However, if the laser is not standard, namely if we have the low Cook cavity, so that the photon lifetime in the cavity is less of the order of the polarization lifetime. That is the phase relaxation time of optical oscillations of active centers in the active media. So in this case, it is the case of so-called superradiant lasers. Under high enough continuous wave CW pumping, we observe via numerical modeling of the Maxwell-Bloch equations that there is spontaneous symmetry breaking of lasing. Namely, the radiation from one end of the cavity becomes much stronger than the radiation from another. And of course, what ends left or right will radiate stronger is 50% probability, because the initial system is symmetric. And that is why we call this phenomenon spontaneous symmetry breaking. The aim of my talk is to explain why it is possible. So, in fact, the explanation will be based on two very well-known phenomena. One is the well-known Rabi oscillations of active centers, which will result in excitation of sideband modes, because if we have homogeneous broadband on spectral line, initially lasing is due to excitation of one central polariton modes. And due to these Rabi oscillations of active centers, there could appear nonlinear excitations of other modes, so that the counter-propagating waves can acquire different phases. And these phases are important in the producing of half-wavelength population inversion gradient due to beating of these counter-propagating waves. And this half-wavelength gradient appears to be very asymmetric, so that the effective reflection of waves from one side of a cavity becomes much stronger than the reflection from the other side in the low Cook cavity. And so the explanation of spontaneous symmetry breaking contains these two phenomena. Let me describe the situation in more details. So here is the schematic design of superradiant laser. I skip a discussion of possible materials which may be used for this superradiant laser. In fact, you know that there are a lot of experiments on superradiant pulse emission with pulse pumping. But if one use continuous wave pumping for this kind of superradiant active medium, then we will come to more or less standard lasing. But in this lasing is specific because the main part of the process is owing to the dynamics of polarization itself, because it weakly decaying as compared to the electromagnetic field in a low Cook cavity. And so the dynamics become different, and due to half-wavelength population inversion gradient, this dynamic may become strongly asymmetric. At the plot on the right, you can see that there could appear this situation, then the wave traveling from the left to right becomes much stronger than the counter-propagating waves alpha minus traveling from the left to the right. And they produce population inversion grating, high wavelength grating, close to the one end of the cavity. And this population inversion grating make it possible the reflections from this end of the cavity to be stronger than from the actual reflections of the Fabry-Perot mirror. And this structure could exist self-consistently forever, although it is self-modulated, because as I will describe, there are Rabi oscillations which leads to different phase modulation of the counter-propagating waves. The main requirement for this regime is the existence of superradiance phase. Here is shown the necessary condition that the relaxation time of polarization should be greater than the so-called inverse cooperative frequency. The cooperative frequency is defined mainly by the density of the active centers and sub-zero and the dipole matrix element of dipole moment of the active centers. And in all slides below, I will normalize the frequencies to the cooperative frequency and also the time to the inverse cooperative frequency and the length to the so-called cooperative length defined by means of this frequency. I should mention that this work is done in collaboration with Ekaterina Kocherovskaya from the same Institute of Applied Physics of the Russian Academy of Science, and from my brother, Professor Vitaly Kocherovsky from the Texas A&M University. And all details related to the specific media which can support this kind of asymmetric lasing you maybe find in our review in the physics of Uspekhi. So I'll skip this and come to the discussion of the fundamental part of the phenomenon. So here are the well-known Maxwell-Bloch equations. In the one-dimensional case, we introduced two counter-propagating waves of electromagnetic field, the corresponding counter-propagating waves of polarization, and also introduced two components of inversion, slowly varying in space, and the amplitude, complex amplitude of the half-wavelength population inversion gradient and sub-z. We have these 6 equations, nonlinear equations for this these 6 independent functions, and in numerical modeling we solve these equations with weak initial conditions using boundary conditions of symmetric Fabry-Perot cavity. And one quantity which we should analyze for the asymmetric lasing is the asymmetry factor of lasing, that is the ratio of the amplitudes of counter-propagating waves at the opposite ends of the cavity. And this ratio may be much greater than unity due to half-wavelength gradient. So in my previous talk, yesterday talk, in the seminar 1, I described the analytic solution to the steady state strongly asymmetric superradial lasing in a slightly asymmetric Fabry-Perot cavity. If the reflection factors of the cavity are different, at least for several percent or maybe in several times, then the solutions can be found analytically, and this is steady state, pure monochromatic solution. It appears that when the reflection factors of the cavities becomes more and more close, that is, we have the limit of symmetric cavity, then this kind of solutions become unstable. And I will describe the reason of this instability and what and the result which we will obtain. But first, let me say some words about this steady state structure in the slightly asymmetric cavity. There are very well located peaks of slow varying population inversion, green here, curve 1, and the amplitudes of half wavelength population inversion gradient, yellow curve 2. This is symmetric curves with respect to the point of peak of these curves. And also there are amplitudes of two counter propagating electromagnetic waves, 5 and 6 curves here, which are also symmetric with respect to these peaks, and counter propagating polarization waves, curves 3 brown and 4 blue here. They also symmetric. And what happens when we have this self-modulated lasing in the pure symmetric cavity? This structure more or less contains the same, but it's oscillate a bit from to the left or to the right, and the amplitudes of both peaks of population inversion and the population inversion gradient oscillate as well a bit. But in general, this structure remains the same, and it remains the same because we have efficient reflection of wave from this population inversion gradient, which makes the effective cavity asymmetric, even if the initial Fabry-Pérot cavity is symmetric. And this asymmetry maintains itself self-consistently and does not destroy it. Of course, if we increase the length of the cavity too much or increase the pumping too much, then far above the lasing threshold, this superradiant stain becomes all unstable and we come from asymmetric lasing to symmetric one. But in the wide range of parameters, this asymmetry exists. And the oscillations of this state is due to Rabi oscillations of active centers, population inversion, and dipole moments of active centers in the field of the central lasing mode. In general, in the active media, there are two kinds of modes, polarization and electromagnetic ones. And in the polarization mode, the main part is played by the oscillations of polarization. And these modes have frequencies close to the resonant transition frequency of two-level active centers. And in the electromagnetic modes, the main part is played by the electromagnetic field, and their frequencies, the frequencies of these modes might be far enough from the resonant frequency of the central mode. But in any case, all these modes, except of central ones, are not in the lasing regime, because for them, in the case of superradiant laser, the lasing threshold is not achieved. So the lasing is achieved only for the one central mode. The amplitude of this mode is very high, and it is quasi-monochromatic. And Rabi oscillations of this mode leads to the nonlinear self-excitation of other polariton or electromagnetic modes. Indeed, you can see that if we have oscillations of population inversion N or population inversion gradient at some Rabi frequency, then the polarization will oscillate not only at the frequency of the central mode, but also at the frequency shifted from the frequency of the central mode to the Rabi frequency. And if at some point on the cavity, in some region of the cavity, the amplitude of the electromagnetic field is such that the Rabi frequency is equal to the frequency difference between the central mode and the sideband polariton or electromagnetic mode, then polarization will oscillate at exactly at the resonance frequency for this sideband mode, and so this polarization will excite this sideband mode. So sideband modes are excited not due to lasers themselves, but due to this nonlinear self-consistent Rabi oscillation. And what we observe in the numerical simulation. In general, we have central peak of lasing modes. In the upper side, it's shown the radiation coming from one end of the cavity, and in the below, it's by blue, they're shown the radiation from the other facet of the cavity. And you see that this radiation is asymmetric, but in addition to the central lasing mode, it contains also some maybe 2 or 3 pairs of polariton modes close to the central resonance frequency, and may also contain pairs of the electromagnetic modes with frequencies at the large distance from the central mode. And its general picture for different parameters of the cavity, you have different numbers of this polariton and electromagnetic modes and different amplitudes of these modes, but in a very wide range of parameters, these oscillations are quite weak. Self-modulation are quite weak, is quite weak, but nevertheless it induce specific phases to the counter-propagating waves. And you see, for example, in this picture, when the peaks are situated close to the right end of the cavity, the snapshot of the counter-propagating waves looks like this. They all the time experience the Bragg reflections from the Hubble wave grating self-consistently, but they also have different phases along the cavity. And because of this, if we calculate the quantity, the ratio of the counter-propagating wave amplitudes at the points, for example, where the amplitude of the maximum electromagnetic wave alpha minus here is minimum. So if you calculate this ratio R at the point of minimum electromagnetic waves, we will see that this effective reflection factor becomes a bit greater than the reflection factor at the facet itself. For example, in this case, you see that this effective reflection factor becomes close to the 0.6 instead of the 0.5 for the Fabry-Perot mirrors. So this means that this side of the cavity becomes higher reflecting than the other side. And so approximately we can apply our analytical solution, and we see that these solutions give rise to the asymmetric lasing. And this ratio are, of course, a complex value due to different phases of counter-propagating waves, and there is at different points it can have this kind of oscillating curves, periodically oscillating curves, but in average this value is higher than the reflection factor of the Fabry-Perot cavity, and this is the reason why asymmetry appears. But this small asymmetry in reflections results in the very strong asymmetry of the radiation from opposite sides of the cavity because we have quite long cavity, and amplification of electromagnetic field inside the cavity is very high. Here you can see the complete description of space-time dynamics, both of phases of counter-propagation waves and amplitudes of counter-propagation polarization waves. But I don't have time to describe them in details. What I should mention that here, by this red colors, is shown the region where the Rabi frequency of the electromagnetic field is exactly equal to the frequency of the one sideband polariton modes. And so it is this region where this polariton mode is excited self-consistently, and this is inevitable feature of this super-radiant asymmetric laser. There is always there are some polariton or electromagnetic modes which are excited due to this Rabi oscillations. There is here, as shown in our example, when we have a sideband polariton modes and their second harmonic, because this is nonlinear regime. And this means that oscillations of counter-propagation waves and also oscillations of population inversion gradient becomes not sinusoidal, but obtain some additional modulation. But in other respects, the situation is the same, and we again have this self-consistent asymmetric super-radiant state inside the cavity and asymmetric lasing in the symmetric cavity. Again, we can calculate this effective reflection factor from one side of the cavity, and it appears 0.8, for example, in this case, although the reflection factor of the mirror was 0.6 actual reflection factor of the Fabry-Perot mirrors. So again, we have self-consistent structure. Here you can see the same situation of asymmetric super-radiant state with multimode polariton spectrum. You see that there are even 3 or 4 pairs of polariton modes, and the effective reflection on the one side of the cavity becomes more complicated. They have more complicated dynamics, but in general, the self-consistent linear Rabi oscillations provides this high reflection factor and strongly asymmetric radiation. You see that there are different periods of oscillations, for example, of a slow varying in space population component of the population inversion in the amplitude of the high-wavelength population inversion gradient. They are modulated with different periods, but in average, the reflection factor is still higher than the reflection factor of the cavity. Also, we analyze the dependence of the this phenomenon of spontaneous symmetry breaking and the resultant super-radiant state on the reflection factor of the cavity and the length on the cavity. And you see that for a wide range of reflection factors, we have more or less similar asymmetric lasing. But of course, when the reflection factor becomes high enough, and so that the photon lifetimes become longer or the order of the polarization lifetime, then this high-wavelength population inversion gradient disappear, becomes too weak to support this regime, and we will observe symmetric lasing in the quite high cavities. Also, if the length of the cavity becomes long enough, then there could appear super-radiant pulses in the central part of the cavity, and also the asymmetric quasi-stationary regime will be destroyed.
Excuse me, I have to ask you to go a little bit fast towards the conclusion, because I think we are a little bit late on the schedule.
Okay, thank you very much. So
apologies for interrupting you.
Okay, the only thing that I will add that we can observe also the case when the not only pre-return modes but also electromagnetic modes are excited, as shown before. And in this case, they should may appear 3 or 4 period modulations and also additional peaks in the high wavelength gradient at that part of the cavity where the Rabi oscillations are resonant with these electromagnetic modes. On the other aspects, the situation is the same. And so let me come to the conclusion. So unlike conventional lasers with high Fabry cavities, the super-radiant lasers with low symmetric cavities at large excess of the laser threshold for sufficiently wide range of parameters of the cavity and active media, the symmetric CD state of pulse generation regime changed to a strongly asymmetric self-modulation quasi-monochromatic regime. So this is very general and fundamental phenomena. And these regimes is due to formation of highly asymmetric high wavelength gradient, as I explained, and the phase modulations of waves, counter-propagating waves, increase the effective reflection factor close to one part end of the cavity, and for a steady state self-modulating separated lasing, according to a number of numerical solutions of the Markov equations, the effective reflection factor at a point with minimum of amplitudes of the one stronger waves becomes from 10th person to several times greater than the actual reflection factor of Fabry-Perot mirror. And such difference is enough to support this strong asymmetric self-modulated separated lasing. So we reveal the mechanism of the spontaneous symmetry breaking of separated lasing in a low co-symmetric Fabry-Perot cavity, and the asymmetric population inversion gradient results in the higher reflections, as I explained, and make it possible to obtain practically unidirectional, weakly varying coherent radiation from the symmetric cavity without using well-reflecting mirrors. Thank you for your attention.
Thank you very much, Professor Koszarowski, for this intriguing description of this instability in super-radiant lasers. I am sorry, I cannot really open the talk for questions because we are already a little bit late. So I think we have to go for the next speaker. I thank you very much again, and we will welcome the next speaker of the session, who is Professor Zverev, I think.
Yes.
Professor Zverev is back. Welcome back, Ben.
Yes.
If you want to close your video, perhaps, Professor Koszarowski, so that the floor is completely to Professor Zverev now. Thank you very much. Yes, please go ahead.
Yes, so do you hear my screen? Yes.
Yes, we do see your screen. Thank you.
Mm-hmm. So the title of my talk is Diode Pumped Neodymium YAG Laser at 4F32 4I132 transition with multi-wavelength output. Co-authors of my talk are Igor Smirnov and Anatoly Sirotkin. And so here is the outline of my talk: motivation, dual wavelength laser concept. Then I will give you some numerical modeling of the laser threshold in neodymium YAG laser with the intracavity etalon. So then there will be some experimental results on multi-wavelength oscillation at 1.3 micrometers, and then there will be conclusion. So okay, I'll continue. So the motivation, then the multi-wavelength lasers are very popular topic for laser physics due to many potential practical applications. They can be used in laser radars in order to compare the reflection signal from two wavelengths and compare and made some comparison. The environmental monitoring that allows you to simultaneously obtain the pollutions of two substances, for example, two impurities, for laser spectroscopy and optic communications. Also, another interesting and rather broad area of application of multi-wavelength lasers are terahertz radiation by difference frequency generation. And for this case, well, for example, if you generate different frequency, for example, for 1047 in ILF laser, 1047 and 1053, you can get the radiation at the frequency of about 1.6 terahertz. So this is a kind of possibility to obtain terahertz radiation. And especially when we talk about this difference frequency radiation, it is necessary to mention that many nonlinear crystals that are effective for this purpose, they are transparent only in infrared, but not in invisible radiation. So, and also if we will talk about the energy efficiency of the DFG, so for infrared radiation, the energy efficiency will be high because you use only the difference of two photons, and if these two photons are in the infrared, so their energy is less, and that's why the efficiency is high. And that's why, well, if we discuss the dual wavelength laser concept, well, there can be different possibilities to produce this dual wavelength radiation. It can be a kind of fixed laser and a tunable optical parametric oscillator, and you can mix them and get dual wavelengths. So there can be two tunable OPOs. They can also provide you a rather broad area of wavelengths, of dual wavelengths. Also, there can be there can be, for example, oscillation in the same laser crystal of two active ions. For example, in 2002, Walsh made some experiments on the laser of oscillating of erbium ions and golmium ions at 2.9 and 2.1 microns in YAG crystal. The system was applied, has some medical applications. Of course, well, it's possible to use the same ion in the laser crystal. For example, for neodymium ions, there were realized dual wavelengths radiation at different levels, ground level, the first, second, and third levels, and especially, for example, for artificial sodium laser star project, well, the sum frequency that gives 1064 and 1318, this gives the radiation exactly for absorption of the sodium in the upper layer of the atmosphere. But in all these cases, it is necessary to mention that for the best conversion efficiency, it is necessary to obtain simultaneously, if in case this is a pulsed radiation, simultaneous radiation and in the same direction. So it should have good spatial and temporal overlapping. And for example, well, also there were some publications on the oscillation with small wavelength difference. For example, when you obtain the radiation in the same energy transition, but at different Stark levels. And for example, this was the work on neodymium in vanadate crystals, and authors used special oriented vanadate, as it is an isotropic crystal, so that the oscillation at 1060 and at the 1067 were the emission cross-section was about the same, and in this case it was possible to obtain the two-photon two wavelength radiation in this system. Well, in all the cases, it is necessary to keep in mind that it is necessary to arrange the conditions so that the amplification gain in the cavity should be the same for two spectral components. For this, well, it's possible to use, for example, the radiation at two polarizations. It's possible to split the radiation by the polarizer. Here is, for example, this is the publication of Dr. Ding with acousto-optic switch. This is one mirror, and two laser crystals are used, and they give the polarizations at different polarizations, and each of the crystals, they are controlled, energy controlled, in order to give a certain inversion in this case, in order to get the same amplification gain for both polarizations. Also, it is possible to use, for example, in vanadates, the anisotropy of the active element. For example, you see here there were some publications, or additional polarizer that can split the radiation in different polarizations and control the amplification gain in each polarization by some intercavity elements. So in our case, we considered the multi-wavelength oscillation at the transition that is also rather popular. This is not the first transition that gives you 1064, but this is transition that gives you radiation about 1.3 in neodymium ions, and in the standard YAG crystal. And typically, well, also it is well known that the emission cross-section at two wavelengths, at the wavelength of 1318 and 1338, has very close values. That's why in most cases, when we have the radiation at about 1.3 from neodymium YAG laser, so it has two spectral components. And sometimes even it is rather difficult to get only one spectral component. But I don't know why, but not many publications are about the oscillation at the third spectral component, that is about 1356 nanometers. It has slightly less emission cross-section. It corresponds to the transition from R1, from the upper laser level, to the X.
Excuse me, Professor Zverev, I did something incorrect, so I removed your screen sharing, but now you have it again.
Yeah, so here is...
I apologize for interrupting.
Mm-hmm. So, and we, in our work, we decided to obtain the multi-wavelength oscillation at these three spectral components. And to make this, it is necessary to somehow to equalize the laser amplification gain in the cavity at these three wavelengths. And we propose to use a Fabry-Perot ettalon, a thin plate, just 100 micrometers, and it was made of pure YAG crystal. This is the scheme that was used in our experiments: electro-optic modulator and the high reflectivity mirror and the output coupler. And what is important, well, we made some numerical calculations, and we considered the transmission through the ettalon at different angles, transmission due to just Fresnel reflection. And here are some formulas that I'm sure that everybody knows. And so if we consider the dependence of the transmission of the ettalon, so we can see that at mostly perpendicular position, so the transmission changes from 100 to about 71%, and oscillate depending on the incident angle. At the angle about 61 degree, we have Brewster angle for YAG material, so the reflectivity is 0, but there is no selectivity. That's why this angle is not interesting for us. If we consider the selectivity of our ettalon, so at small angles, there is this red, green, and blue curves. They show the transmission of ettalon for different wavelengths. And you can see that it varies, and it varies very strongly, and it depends on the wavelength very strongly. So we decided to introduce these losses into the cavity, into our cavity, and made calculations of the threshold pump intensity for certain spectral component. These values were used in order to proceed our calculations. Well, normally the publications that consider some numerical modeling for dual wavelength operation, they compare these threshold intensities at two spectral components. But in our case, we considered to use not a ratio, but the difference, as I show you further in my further slides. So here is the slides that gives us the values of the threshold intensity of neodymium YAG at different spectral components. Here we can see that the threshold oscillates and it increases almost twice from 0.08 to 0.14 value. This was made for 1318 nanometer. And here are the here are the dependencies of the thresholds for other spectral components. So in principle, what we need is we need to find the position where there are the intersection of the thresholds for different spectral components. But it is necessary to note that if there is a kind of cross, like here, for example, it is very difficult to satisfy this condition, because slight change of the angle due to due to the some mode in the cavity, and so some angular dependence of the mode transmission in the cavity results in the change of the angle, and so it will have higher losses than it should be. Anyway, well, there is, for example, the point about 4.5 degrees that three wavelengths, they have cross section, so three wavelengths operation can be obtained in this case. So if we consider the difference of the threshold intensities, so we can see that here are differences for two wavelengths, 1318 and 1338. So there are some positions with the angles about 11, 26, 36, 45 degrees that have difference of about 0, and this difference is rather broad in the angular, speaking about the angular. So it is from, for example, from 10 to 12. Here is exact position is 26, but in reality it is a little bit broader. And in this case, we calculated these differences for different combination of our samples of our spectral components. And what is interesting that in case of 11 and 26 with this blue line, I showed the positions that the difference of the thresholds are about 0 for both, for all three components, and at these angles there should be conditions for obtaining the three wavelength oscillation. And we tested this in our experiments. Here is our experiments based on the side pump, diode pumped wave laser, neodymium YAG laser. It has 10 centimeters long active element with 4 millimeters in diameter. And this is the one mirror, this is the Fabry-Perot echelon, and this is the electro-optic modulator and the output mirror. And so we checked the operation, and we found that really it is possible to obtain dual wavelength operation at the angles that were theoretically predicted. Here are another combination and also another combination of wavelengths. And at the wavelengths 4.7 and 12 and 27 degrees, it was possible to obtain the three wavelength operation of this multi-wavelength laser. And also we measured the efficiency, of course, of our laser. This is the efficiency of just the single wavelength operation, and this is the efficiency of the dual wavelength operation. You can see that the most efficient case is to obtain the 1318 and 1338. Of course, they have much higher emission cross-section, and that's why it has much more intense energy. The pump energy that is the electrical pump energy that is brought to the diode bars of our optical chamber, and so we can tell the efficiency from electricity in our case was maximum efficiency was 3.5%, This is slope efficiency, and the efficiency of the triple wavelength oscillation. This is the green line. It was about 2.4%. We checked the temporal shape of our dual wavelength laser. It was about 37%, and similar temporal shapes for 3 wavelengths operation laser. And we checked the simultaneous operation of our laser at different wavelengths, and we measured this in the second harmonic generation. So we got the some frequency generation with higher efficiency than the some frequency of the each separate wavelengths. So, and finally to the conclusion, so we proposed and we showed that it is possible to control and to develop the laser, multi-wavelength laser, by using the intracavity etalon and by tuning the incident angle of the etalon, intracavity etalon. It is possible to obtain either single or dual or triple laser oscillation. And well, the slope efficiency was rather high in our cases, about 2.4 for triple wavelength oscillation. And for dual wavelength, well, the efficiency was about 2.5, and the maximum output energy was 150 millijoule when pumped with the 8.7 joule of electrical pumping. So I think that this system is rather promising in order to obtain and to control the output laser radiation, spectral output of the lasers. And thank you for your attention.
Okay, thank you, Professor Zverev, for this remarkable achievement. I am the same person, but from another computer, so I apologize for that. We shall take time for one brief question. If there are questions, please either take voice or raise your hand, up to you.
Yes.
May I ask a question?
Yes,
Sure,
please go
yes.
ahead, Professor Kosharovsky.
In your remarkable triple wavelength operation, what was the polarization in each wavelength? And is it possible to have different polarizations at different wavelengths, or even control this polarization?
Well, in our case, of course, we have the same polarization for all spectral components because we use the electro-optical Q-switch with Brewster cut angles. And in principle, well, I think it is possible to, as neodymium YAG is isotropic, it is possible to obtain different polarizations for all these components. Well, however, it's necessary to keep in mind that we considered our Fabry-Perot etalon as it operates for p-polarization. So you see, when you have perpendicular polarization, so the dependence will be different. So it is necessary to think about this, and this is a good question, and we need to think about this. Thank you. Yeah.
Thank you very much.
Okay, thank you. If there is one last short question, then we take it, and if not, we conclude.
May I? Thank you very much. I'm very impressed. I'm not familiar with the topic at all. Are there other laser systems that can operate on 3 wavelengths simultaneously?
Well, there are some publications about this. Yeah, and well, for example, our system operates, and well, just I don't know. I don't know. Maybe there are not. Well, it's a good question. I need to think.
Thank you anyway. It was very impressive. Thank you very much. I never heard of 3 simultaneously. Thanks.
Okay, well, that is probably a good conclusion then for this session. I thank all speakers and all participants for taking part, and Gianluca, of course, for putting together this opportunity to meet all here. And we can meet again in 1 hour and a half or so for the next session of this 4th workshop. Thank you very much. Goodbye.
Thank you. Goodbye.